Good evening. It's not often we can begin a sky at night with a really exciting discovery, but this time we certainly can. English astronomers have discovered by far the most massive and the most luminous star in the entire galaxy. Now remember, a star is a globe of gas, and our Sun is a very ordinary star. But this new discovery is different. It's known officially as R136a. I'm going to call it the monster. Its mass is 265 times that of the Sun, and it shines 10 million times more brilliantly. The discovery was made by a team from Sheffield, led by Professor Paul Crowther and Dr. Richard Parker. Richard Parker's come down here specially to join Chris and me. We are very grateful. Thank you so much for coming.
It's a pleasure.
This is really exciting. Can you tell us exactly what the monster is and what's so unusual about it?
Well, Patrick, the monster star is the most massive member of the star cluster R136 in the Tarantula Nebula. Now, this star cluster is located in the Large Magellanic Cloud, which is a satellite galaxy of our Milky Way. And up until now, we've not really been able to fully resolve the individual objects, and certainly we haven't been able to get an accurate determination of the masses of these objects. We actually have an animation of the object here. And what we're actually doing is stepping through the Tarantula Nebula, and the cluster of stars that we were observing, you can see, is right at the center here. And it's absolutely incredible. We can go from outside right in, and this is giving you a demonstration of how difficult it was to get the resolution required to pinpoint them as being individual. And I believe our object is this one over here.
That's the monster.
That's the monster, with a very close companion.
Our Sun is a very modest star. Even so, it's a great deal bigger than the Earth.
Indeed, and just to give you some idea of the scale, I have in my hand a small peppercorn, and this represents the Earth. On the same scale we have the Sun, shown by this globe. And then if we take the scale even further up, we replace the Sun with a coin, and then this globe then becomes the star R136a, the monster star.
So it really is very large, but it's also massive.
It is incredibly massive. It's believed to be 265 times the mass of the Sun.
That's the whole point, isn't it? No one believed there could be a star as massive as that. Anything more than 150 masses of the Sun would blow itself to bits, and the monster hasn't.
It hasn't, and we're at a loss to really work out why it hasn't. Our idea for star formation is probably different from how we assume the Sun formed. We assume the Sun formed from the collapse of a gravitationally bound cloud of gas. The monster star, on the other hand, probably formed via the merger of several stars. The cluster, we know, is very dense and probably is undergoing very violent dynamical interactions with the stars all having a gravitational influence on each other. And we're, at the moment, postulating that it could be the result of mergers of stars. And we have other researchers, both in the UK and around the world, working on hydrodynamical simulations of such an event.
What was the previous record for the mass?
The previous record for the mass was in the Arches cluster, which is near the centre of our galaxy, the Milky Way. And the record was that one of these stars probably was around 150 solar masses at its birth. These three stars in R136 were respectively 320, 240 and 220 times the mass of the Sun at birth.
Well, there is the monster. Why hasn't it been identified before?
Simply because we couldn't look deep enough. We've been using the Very Large Telescope in ESO in Chile, coupled with a brand new instrument called the Multi-Conjugate Adaptive Optics Demonstrator, or MAD for short. As you say, it's a very dense, very bright, luminous environment, and we were actually more interested in the dynamics of these systems.
Because how the stars move.
Exactly, because we're particularly interested to find out what the birth environment of other stars, even stars like our Sun, was, because we think that the majority of stars form in clusters, and presumably the other stars in the cluster have some influence on young suns and possibly their protoplanetary systems when they're forming. And we were almost by serendipity decided to recalibrate and recalculate the mass of these stars, and this is how we derived our result.
It was 169,000 light years away, and 1 light year is 6 million miles. It's not on our doorstep.
People actually used to think this whole cluster was one star, didn't they?
Exactly, yeah. In the 1980s, there was a large school of thought that suggested that it was a 1,000 solar mass star, and it was only really in the 1990s, with the advent of the Hubble Space Telescope, that we were able to resolve the individual components. Even then, it was incredibly difficult to really kind of get a handle on the mass. And what we found is the three components of this R136 cluster are three massive stars, 265 solar masses, and then two others which are still well above 150 solar masses.
Huge red supergiants like Betelgeuse are cool by comparison, but this one is different because it's not cool and red, it's very, very hot.
It's roughly 55,000 centigrade. This compares to only around 6,000 centigrade, which is the temperature of the surface of the Sun.
Well, look, our Sun is losing mass at the rate of 4 million tonnes per second, but the monster is losing far more than that.
It certainly is. It's losing the equivalent of an Earth mass per year.
So if you work that out, I reckon roughly in the time it takes to watch a sky at night, it will lose something like 10 million billion tonnes of matter. So that's quite a rate.
Yes.
And does that have any effect on the surroundings? If you're pumping that amount of material out, surely you might be able to see that.
It does. It's an incredibly violent stellar wind, the kind of expulsion of material from stars. And some stars like the Sun, the more modest mass stars, when you have an outburst of a stellar wind, that can cause problems with communications here on Earth. But I'd imagine if you were anywhere near this star and being subjected to this stellar wind, it really would be quite a horrific experience.
Well, I remember a thing called the Eddington limit. Sir Arthur Eddington, whom I didn't know, he worked out that you couldn't have a star more than 150 times as massive as the Sun because it would be unstable. Well, this has shown that's wrong.
Yeah, it has. This 265 solar mass star, we believe, was 320 solar masses originally at its birth. We were struggling to explain how we form massive stars of 10 solar masses and above, and this really is just posed us an even bigger problem.
Because the problem is that you form stars by having material collapse down upon themselves deep within a nebula, and that works really well, except that eventually you get a dense enough centre to the core that you start the star's formation. Once the star ignites, it's very hard to force more material down onto it. So it's very hard to understand how this thing didn't ignite and stop its collapse well before it got to 150.
Well, the monster lies in a different galaxy, a satellite galaxy of ours, the LMC. Can we find any monsters in our own Milky Way system, do you think?
It's certainly possible. What we have, if you look towards the centre of the galaxy, we have a great deal of cosmic dust, which of course reduces the amount of light that we can see coming from star clusters on Earth. The other thing is that most star clusters in the centre of the Milky Way are just simply too old to still be hosting these massive stars.
Well, when I began this programme, I said this is a really exciting discovery, and it most certainly is, but in what way is it going to alter your ideas of stellar evolution, of the way stars are born, how they behave and how they die?
I think one of the major things is that a lot of theories of how more modest star clusters, such as Orion, evolve, and also the environment that we think that most stars must form in, is in many ways governed by this upper mass limit of 150 solar masses. We describe if you count all the stars and put their masses into different categories, we get what's called initial mass function. And those initial mass functions are always capped at 150 solar masses. And we use these initial mass functions in our theories of evolution of clusters, the kind of picking different environments for star formation to occur.
When you look at different galaxies.
Exactly. And it really is a kind of a fundamental building block of both galactic astronomy and extragalactic astronomy.
You have a small telescope, a reasonable one, and you want to go and have a look at the monster. Where have you got to go first? Well, how far south?
A fair way into the southern hemisphere, so perhaps Chile or northern Central America, perhaps central southern Africa, perhaps, and certainly Australia.
And then with your small telescope, what are you going to see?
I don't think you're going to see much, unfortunately. This cluster is incredibly difficult to resolve even with an 8-metre class telescope. However, the Tarantula Nebula, within which it's located, is a really beautiful feature of the night sky.
And then this cluster's right at the centre of
That's
the
right,
tarantula
yeah.
as well.
Yeah.
So you can at least look at the region and know that the monster's there.
You know, Chris, I wonder what the sky would be like if you could get anywhere near that region.
Well, it would be spectacular, wouldn't it? I mean, you keep mentioning Betelgeuse, which is a
Yes.
luminous, massive star, or think about Deneb, which is probably the most luminous of the really bright naked eye stars. That's what, 70,000 times
About
as
that.
luminous
More
as
than
the
that
sun?
now, yes.
But that pales. What did you say the luminosity was?
10,000 times that of the sun.
Okay, so maybe my number for Deneb.
10 million, isn't it?
10 million, sorry.
10 million, there you go.
million,
Yeah,
10
no,
million.
we've got to give the monster full,
Yeah,
full
no,
credit.
yeah.
Our Earth is nearly 5,000 million years old. The sun's older than that. But the monster certainly isn't.
It isn't. It's relatively young, almost a baby in comparison to the Earth and the Sun. It's only 1.5 million years old, and we don't believe that it will live for much longer than a few more million years after that. So we really are just looking at a very fortunate window of this cluster's evolution to be able to detect stars of this mass. And also, I think that the cluster is very massive in itself. It's much more massive than most star clusters nearby in the Milky Way, such as the Orion Nebula cluster, Taurus, for example, is a very low-mass star formation region. So I think it's unlikely that you'll have that much stellar material in one place too often.
But this is what we call a superstar cluster, right? And we see these in other starburst galaxies, galaxies that are forming huge numbers of stars. So, I mean, is this a typical example of what we might see in galaxies like M82 and other places where there are fireworks going on?
It's a very good question. I would expect this to happen in other places, but of course one of the problems is that we can't really observe those more distant locations in enough detail to be able to say for certain whether or not you have stars that are 100 solar masses and above, and how many of these stars we have. We expect this to undergo a supernova explosion within a few million years, and up until recently, other groups of researchers have been putting forward ideas of something called a pair instability supernovae, where a very massive star will explode and leave no remnant, for example, a gamma ray burst or a black hole or a neutron star. All that will happen is that this star will explode and then populate the local environment with some very heavy chemical elements such as iron, silicon and carbon, but leaves no trace of ever being a star.
One thing that I think is important is what effect these stars, if there are these 250, 300 mass stars, maybe only a few per galaxy, but they could have a really important effect on the rest of the galaxy by seeding them with these heavy elements. You talked about getting iron out there. If they're this big and they explode in this special supernova that doesn't form a black hole, doesn't form a neutron star, but pushes the elements out, everything it's got out into the environment, that may be the solution to where some of these heavy elements come from. You probably don't need that many of them to have a significant effect on, certainly on a galaxy the size of the LMC.
How surprised are you to find a thing like the monster?
I was very surprised. I have to confess that I'm not a seasoned observer. I'm a theoretician. And when Professor Crowther first put it to me that there may be stars of 300 solar masses residing in this cluster, I went and advised him to go and check his calculations again. However, if you do not limit the mass function of the stars around us to 150 solar masses, if you choose 300 or 350 solar masses, you can form such massive stars if you have a cluster big enough, and R136 cluster, as we've discussed, is indeed big enough.
Would you say that the identification of the monster is one of the most important things that happened in recent times?
I don't want to blow our own trumpet too much, but I think that anything of this scale really can only be good for both the astronomical community in general and UK astronomy. I mean, I think it's just a fundamental importance that we keep on asking questions in our field. It's such a trough to get into, to assume that you've reached the limit of something. You've got to 150 solar masses. The fact that we can't explain even 150 solar mass stars should not deter us from trying to find something even bigger, because these, again, as Chris is saying, are asking the fundamental questions of what implication does this have for forming life, not just in our galaxy but in other galaxies, and you know, how many planetary systems can possibly form in our galaxy and in other galaxies.
Well, there it is, and the monster will lead you on to other great discoveries. Richard, thank you so much for coming down. We are truly grateful to you. Many thanks indeed. Well, interesting things are going to happen. We are coming in now into the start of the Perseid meteor shower. So let's go out into the garden and join Pete and Paul.
Hi, Paul.
Hi Pete, how's things?
Fine, thank you. It's a lovely night.
Yes, it is a lovely August night here in 𝐶𝐶, and that means one thing, the Perseid meteor shower.
Of course.
And of course we know that a shower is caused by the Earth passing into the debris of a comet. In this case it's Swift-Tuttle, isn't it?
It is, that's right. Comet Swift-Tuttle, which was discovered in 1862 by Lewis Swift and Horace Tuttle.
What a wonderful name.
But yeah, a comet leaves a load of particles in its orbit, and as the Earth passes through the orbit of a comet, those particles, which are known as meteoroids, actually encounter the Earth. It's basically, as they come through the atmosphere, they compress the air in front of them, and that heats the air up. The air is then able to put enough heat back to vaporize the front surface of the meteoroids, and they give off light, and you see that light given off as the meteor trail.
It's quite impressive sight, isn't it? Some of the big bright ones, trail can be very, very long indeed.
When you get a big bright one, you also get a bit of a bonus sometimes as well, because there's enough ionisation there, enough excitation of those atoms, that when the meteor trail has actually gone by, you're actually left with a column of glowing air behind.
Which is, of course, the meteor train.
That's known as the meteor train, and you can see that sometimes left behind after a bright meteor.
So when would be the best time to look at this, do you think?
Well, the Perseids are actually active from the 23rd of July through to the 20th of August.
That's quite a long period, isn't it?
It is, but it's only when you get right into the very centre, which centres this year on the night of the 12th, 13th of August, that you start to get some very good rates, up to 100 plus meteors an hour. But if it's cloudy and you miss that night, a couple of nights either side of that are also normally pretty good.
So it's worth looking really around the whole weekend, isn't it?
Yeah.
And of course you don't need much in the way of specialist equipment, do you, for observing meteors? I think this is one of the wonderful things. A comfortable chair, some warm clothing perhaps?
Well, the most essential thing you need to do first of all is to actually find a location which is dark without any stray lights.
Well, here we are, Pete. We're dark adapted. We've got a beautiful view of the sky. I think out of all of the activities that the amateur astronomer can engage in, I think meteor observing is the most sociable. And I love to have friends around and we concentrate on particular areas of the sky and make observations of various meteors. It's a wonderful thing to do.
That's right. You can either do it seriously, scientifically, or you can just go out and enjoy the wonders of the night sky.
Now, the Perseids are called the Perseids because they appear to come from the direction of the constellation of Perseus, don't they?
That's right. Basically, as the Earth travels through the debris stream left by Comet Swift-Tuttle, even though all the meteoroids in that stream are travelling effectively in parallel orbits, as they come through our atmosphere, perspective effect makes it look as if they're all coming out from the same point in the sky, which is known as the shower radiant.
Now, of course, the radiant itself isn't a good place to look for the meteors, is it?
If you look at the summer triangle where the Milky Way passes through, that's a good place to look, around the constellation of Cygnus. But after that, as you go through until the dawn hours, if you're up that late, then switch your view round to, say, look at Pegasus, the flying horse. The peak of activity is on the night of the 12th, 13th of August. Now, there is actually a shift in the number of meteors you can see and the brightness of the meteors you see after midnight GMT. And the reason for that is quite simple, because before midnight GMT, the meteoroids actually have to play catch-up with the Earth to actually enter the atmosphere.
Yes, indeed.
But after midnight GMT, the Earth has turned round, so it's actually encountering the meteoroid particles head-on.
So they'll be brighter and more spectacular.
There's a greater collision energy, and they are brighter, yeah, that's right. And I like to lie out in August and just take in the beauty of the shower, but I know that you actually want to do some science.
I do. I don't just want to lie here. And I have here a very, very useful form. This comes from the meteor section of the British Astronomical Association. And on it there's various columns for recording the time of your observation, estimated brightness of the meteor, the constellation it comes in. And from this we can deduce a lot of information, a lot of very useful information, like count rates, which are very important, aren't they?
That's right. I mean, if you've got the number of meteors which are coming down, which actually belong to the Perseid shower, you can actually use that data to work out a model, if you like, of the debris streams which we're passing through.
Well, of course, if you get tired of observing the Perseids, The bright planet Jupiter's making a comeback, isn't it? It rises before midnight now and is visible low down in the southeast sky, isn't it?
It's unmissable, really. It's so bright. It's the brightest thing in
And
that
a lovely
area.
yellow colour.
It is, but if you've got a telescope, say a 10-inch or larger, and you look at Jupiter on the early morning of the 14th of August, say from about 2:40 BST, you should be able to see the bright moon Europa approach the planet's disk. Now, what Europa will do, it'll actually catch up with Jupiter, pass across the front of the disk, and then exit off the other side. But as it does so, the Great Red Spot should also be visible on the planet's
that'd
disk.
be interesting.
And Europa should actually catch up with the Great Red Spot, or appear to catch up with the Great Red Spot, and then pass across it. I really hope it's clear, though.
Yeah, so do I. Oh, there's one.
Oh, yeah.
Well, let's hope for the Perseans. Indoors now for our news notes. Chris Linton and myself, and joined by Chris North from Cardiff. And first of all, the Planck telescope. And Chris, this is your province.
Yes, the Planck telescope was a satellite that was launched in May 2009, so it's been up there just over a year by now. And it started its observations in about August, and the first 10 months of observations have just been released in this image. Now, the main thing you can see in this image is it's the entire sky. It's flattened out into an oval. And the main thing you can see in it is our own galaxy, the Milky Way. It's a white strip across the centre, and then the blue wispy stuff above and below is much closer material, just above and below the plane of our galaxy, essentially above and below the Earth. The real thing that Planck's after, though, is actually visible in the top and bottom of this image. It's the red and yellow mottled appearance is something called the cosmic microwave background. Now, this is microwave radiation from the very, very early universe, from a few 100,000 years after the Big Bang. And encoded in the pattern of the cosmic microwave background is lots of information about how the universe evolved in its earliest stages, and also what the universe is made of, how much of it is mysterious dark matter and dark energy, and so on. And so by looking at that information and being able to peer through the galaxy and work out what's the galaxy and what's the distant universe, Planck can make an excellent image of this microwave background and establish some of these numbers better than we know them at present.
And astronomers like me get a beautiful shot of the Milky Way and a lot of information about our galaxy as well, so everyone's
Indeed.
happy.
In this image you can see an enormous span of time. You can see some of the bits of our galaxy, there are stars forming right now, and Planck is seeing that. And it's also seeing the very early universe. So it's 13.7 billion years all in one image.
It's going well. Meanwhile, now, back inside the solar system, we've had a total eclipse of the sun, visible from Easter Island. How I wish I'd been there.
Yes, this was a tricky one. It only just made landfall. You could only see it from land right down in the very tip of South America. And I think probably this is the eclipse in the last 50 years that was seen by fewest people,
Right, yes.
I would bet. Maybe some of the Antarctic ones. However, some people did make it down there. They're a very popular site, partly for convenience, but partly for the atmosphere, was Easter Island. And it must have been an amazing experience
quite incredible.
to watch the moon pass in front of the sun from there. We have had some beautiful images back, as you can see. You can see the pearly white of the sun's corona, the outer atmosphere, and actually a couple of prominences visible, the purple flames reaching up above the moon's limb. So a beautiful eclipse. Sadly, I wasn't there. Maybe the next one.
I wish I'd seen it. Another thing, Rosetta space probe, it's past the asteroid Lutetia and sent back rather interesting pictures.
Yes, this is fascinating. Rosetta, of course, is the European Space Agency's comet-chasing spacecraft. It's on its way to comet 𝐒𝐿 and Churi to its friends, and it'll arrive there in 2014. But on the way, it's past actually the largest asteroid yet visited by any spacecraft, and it's an interesting world. It's got a large impact basin, so a place where something's hit it and left a crater. But also, look at these. This is a close-up from some of the images. Can you see these grooves that are on there?
Indeed.
Now, they look rather familiar to me because they look rather like grooves that we see on Phobos, the moon of Mars, which is a captured asteroid. And I don't think it's very well understood where those grooves come from, but I'm sure scientists who've only just got these images will be poring over them.
Another probe, of course, is Messenger, and that's concerned with Mercury. And it now seems that Mercury may be more active volcanically rather later than we thought.
Yes, really surprisingly late. Messenger's just had its third flyby of Mercury back in 2009. It'll go into orbit around Mercury next year, and then we'll know more. But the results from this flyby have found a region which is very fresh by Mercurian standards anyway. It's a place called Rachmaninoff.
Yes.
named after the composer.
Yes.
And it seems that this may have been laid down as recently as a couple of billion years ago.
know.
Now that sounds like a long time ago, but most of Mercury is much older,
Oh, yes,
3-4 billion years. So this is quite an interesting discovery. And I think when Messenger gets into orbit and we start getting really detailed pictures of most of the
Yes.
surface, I think Mercury's got a few surprises
Oh,
in
it
store.
has, I'm sure. Another probe still working well is, of course, Cassini, orbiting Saturn and its moons, has made a special study of Titan, the world with the lakes of liquid methane. And one of these lakes is evaporating, but it doesn't mean it's going to be lost.
No, this is just what summer on Titan is like, Patrick. So the lake in question is Ontario Lacus, down in the southern hemisphere. We're just past midsummer, but in the 6 years that Cassini's been there, the surface of the lake has actually dropped by 1 metre. And we can measure that through measurements done by Cassini as it flies past. Now that methane will evaporate up into the atmosphere, presumably be carried elsewhere on Titan, and it will fall as rain, maybe in the northern hemisphere, which is in the middle of winter. And so we're seeing a real methane cycle, just like you learned in school with water. Water evaporates on the Earth, and it rains, it flows down through rivers to lakes and seas, and then evaporates again. And exactly the same process is happening on Titan.
I think Titan must be rather a dismal world with a constant methane drizzle from the clouds above.
Yeah, not very cheerful, but an incredibly interesting
yes.
place. This mix of chemistry isn't something that happens anywhere else in the solar system. It may be a little like the early Earth was. And so I think Titan's a really good laboratory for trying to understand what primitive chemistry on a planet, or in this case a moon, looks like. And people are doing all sorts of experiments to work out exactly how we account for the chemistry we see, whether life could have formed with this mix of chemicals, and exactly how the methane moves from the lakes to the atmospheres. But you have to think, before Cassini got there, and before it dropped the Huygens probe down into Titan's clouds, we didn't even know what the surface of Titan was like. We didn't know if it was completely covered by an ocean, whether it was completely solid. And now we have this really dynamic world with rivers and lakes and rain. It is absolutely wonderful.
It's a weird place. Then what about the snowballs in the ring? These are a shock too.
Yes, absolutely. In fact, way out in the F ring, which is the outermost and most tenuous of Saturn's main rings, shepherded by a couple of small moons, so Prometheus and Pandora. And in particular, as Prometheus goes round the planet Saturn, you see material in the F ring sloshing together. And it seems that sometimes it forms these little snowballs, maybe 12 miles across or something like that. Now, these may just disperse. After all, snowballs aren't particularly solid things. Or maybe this is the beginning of a process that would lead to forming a moon. And so you start off with one of these sloshy snowballs, and it might collect other material and get bigger and bigger. And maybe some of the small moons that we see in Saturn's system formed this way.
They probably did. And certainly Cassini had been a tremendous success. Chris, thank you very much. And when I come back next month, we'll be talking about events on Jupiter. So until then, good night.
Dan Snow sets off on the first of his Norman walks here on BBC4 this evening at 10. That's here after another chance to see Britain's Park Story with Dan Cruikshank next.